stuff, because I'll do that once I see it pop up in my.
Okay.
Just let me know when the video is going.
Let you know what? When
Let
it
me know when
starts?
it kicks you back to the YouTube page and you see the video up there. Once I see it pop up in my. Oh, sounds like it's working. Just let me know when the video is going. Yeah, so you can go ahead and close out of that or mute that.
Let you know what? When
Let me know when it kicks you back.
Hold on, it's doing good. So I can just get out of this.
Oh, yeah, go ahead and get out of that.
There. Okay.
And then yeah, so I got it pulled up now, so I'm gonna edit and add the title and description stuff.
Now it says when system dialog prompts, click open Zoom meetings. When system dialog prompts, click open Zoom meetings. Oh. Well, I just went back to this.
So yeah, so I can't add the whole title, so I'm gonna add. I'm just gonna pull a little bit.
Well, that Noah guy was happy, so that's good.
All right, well, I think we should be good. So I edited the title and put some stuff in there, and I added links to the YouTube and put it on the Twitter page as well.
Okay, I need to make him a co-host. Hi, is it Sanjiv? Let's unmute you, Sanjiv.
Can you hear me now?
Yes. Is that how you pronounce your name?
Yes, that's right.
Awesome. And you just changed it, right? Because I made you co-host and I was like, oh, maybe that's not him. So let me make you a co-host again.
Yeah.
There you go.
Yeah, that was my daughter's name.
Hi, Sanjiv. Tracy.
Hi, how are you?
Good. How are you?
Doing good, thank you. Yeah, I thought I'll join a little earlier so that technology works fine.
Yeah,
That's
I'm glad
good,
you
yeah.
guys are so fast. You already have it set up. That's great.
Yeah, Ryan's doing a few things to get some other stuff. So
Some other stuff set up.
well, we're trying to do live on YouTube.
Oh,
So that
okay.
Noah people can join and some others. So
Yeah, I see it up in the left-hand corner of my screen. Yeah.
I just haven't advertised it fully because it's not perfect yet.
Yeah. But these also go up on the website, right? The recordings?
Correct.
Okay. So Tracy, do you think I should go over any Zoom ground rules, or do you think people are pretty well versed by now?
I think it's good just to mention, you know, that everybody should have their video off. If they don't,
Yeah.
if they don't have it off, I will turn it off, and to be muted, or I'll mute them. And then if they have any questions, to wait to the end and just have their hand raised.
Cool.
Yeah.
Sanjiv, I have a question for you, actually.
Yes.
I've always wondered, I've heard this acronym pronounced multiple ways. Is it GLACE or is it Class A?
Yeah, I pronounce as GLACE.
Okay.
But its original creator, Randy Koster from NASA, he pronounced it gloss. I never got that pronunciation. So for me, it is glaze.
Okay, that's what I'll use then.
Yeah, I asked once Paul Dermeyer from GMU why it is called gloss. So he said, Randy is from France, so he uses the pronunciation from the France. So.
Got it. Yeah, because I'm pretty sure I've heard it both ways, and I wasn't sure. Yeah.
So Ryan, everything looked good for YouTube then?
Yep, everything's good.
And then I'll just hit record and we're good to go then, right?
Yeah, I mean, I'll hang out till around 11:30, but I got another
Okay.
meeting. And then, yeah, I'll stop sharing at 11, so it's like.
Okay.
So I have a question for KT. Is that how I pronounce your name?
Yeah.
So like, should I leave like last 5 minutes or 10 minutes for the questions?
Oh yeah, good question. I mean, I think 5 to 10 minutes is a good amount to aim for. Definitely at least 5 to 10 minutes, so that we make sure we can have some discussion.
Oh, thank you.
Yeah, sure. All right, so folks are slowly trickling in, but I think we'll get started if that's okay with you, Sanjiv, and go over a few logistics first, and then I'll introduce our speaker and hand it over to you. So welcome everyone. Thanks for being here. Welcome to a new year of CGD seminars. Hope everyone is doing well. So we're going to be on Zoom for the time being. So luckily, I think most folks are pretty used to this format by now. I wanted to mention a couple of announcements and just go over some quick ground rules before introducing our speaker. So we do have two seminar slots open for the fall. One is in 2 weeks on September 29th, and one is on October 20th. So please let me know if you're interested or you know anyone who might be interested in filling those slots. We also have a really open schedule for winter, spring 2021. So if you're looking to present further out, that's an option as well. Okay, so just some Zoom logistics. I know a lot of you are familiar with this, but try and keep your video off during the presentation and make sure that you're muted. This is being recorded, so it'll be posted later. And then during the question and answer portion at the end, you can either raise your hand, which is a feature, I believe, under the participants window, or you can type your question into the chat box. And then finally, during the discussion, just please remember to be respectful and share the air. So it's my pleasure to introduce Dr. Sanjiv Kumar as our first seminar speaker of the year. Dr. Kumar is an assistant professor at Auburn University, where he leads the Climate, Water, and Society Lab. He received his PhD in hydroclimatology from Purdue University in 2011. After postdoctoral appointments at the Center for Ocean, Land, Atmosphere Studies, Pacific Climate Impact Consortium, and NOAA Esrael, he joined Auburn University in 2017. His research focuses on modeling land-climate interactions, including feedbacks to water, agriculture, and forest resources. So today he'll be presenting on the GLACE-Hydrology Experiment, effects of land-atmosphere coupling on soil moisture and variability. So Sanjiv, the floor is yours.
Thank you, Katie, and thanks for this opportunity. Let me share my screen. So I'm not able to share my PowerPoint.
So you had it up there before, right? When I joined.
Okay, let's.
So Sanjiv, if you take your pointer and go down to the bottom, do you have a bar that gives you a bunch of options? And it says share screen in the middle?
Yes.
Yeah.
Change PowerPoint, share. Yeah, okay, now I can. Okay, can you see my slide now?
Yeah, that looks good. You could put it, and now it's in presenter mode, so that looks good. Yeah, thanks.
Okay, very good. So yeah, thank you, and thanks for this opportunity. Today I'm going to talk about the GLACE-Hydrology Experiment. I have presented this experiment a couple of times in land model working group. So now in the last 2 years, so now this experiment has been published in Journal of Climate. So I thought maybe putting together all those talk into a single talk would be a good idea. And this talk is more geared towards like a broader community or climate science community. Yeah, if you are interested in details, yeah, there is a paper in Journal of Climate. I thank all the co-authors. That's a long list there. Go next. Okay, so this is our view. I'll talk about motivation and historical context. That means GLACE experiment has been here for more than a decade. So I'll talk about how does this new experiment fit into that GLACE family of experiment. Then GLACE-Hydrology Experiment design and data availability. It's a combination of 4 experiments, and then that took us a little bit time to explain. So that's why I will spend some time in its design and where we can you can get the data. And then most of the time that I will spend on the budget equation for soil moisture variability. This is one equation that I want to convey through this seminar. This is a very important equation, and all the slides will try to fit into this equation. So we'll explain in detail. Then what is the new result from this experiment and implication for drought predictability. So the first 4 points have been published in Journal of Climate, and as you will see, once we'll go to the number 5, it became too long. So basically the BR said, okay, publish it in the next paper. So I'll cover number 5, but we are still working on for that number 5 for a separate paper. Okay, so what is scientific inquiry here? So in terms of what I remember back in 2015, I was applying for the NRC postdoc. And then Matt Newman from NOVA, he asked me, okay, given my background in hydrology and water resources, what I can uniquely bring into the table, or what I can uniquely bring in the perspective. And it took me just 5 minutes to think about, okay, I'll investigate how does the land atmosphere coupling impact the land variability. What does that land mean? It means the soil moisture, it means the water resources, it means the vegetation variability and predictability. It didn't take me more than 5 minutes to think about or conceptualize this idea, but it took me 5 years from that conceptualization to the publication. So it takes some time, and it's a little bit complicated experiment. So as I'll explain the experiment, you'll realize why it took us little time to publish it. So goal is, yes, how does it impact the drought? How does it impact the water resources, variability and predictability both? If we distill down that question to a little more detail, what you see in this figure is the 2012 drought. This is one of the most spatially extensive drought in the United States. A greater part of the United States is in this drought. So the question we can ask, can we predict these large-scale drought, particularly in that Great Plain box that I saw in this box region here? And the second important question for this study was, what role do the land atmosphere coupling play in a large-scale drought in the Great Plains? So we will focus on this box region, particularly for that point number 5 that I was describing in overview slide. So these are 2 motivating questions, or the scientific question that we are going to address in this presentation. To give you a historical context, why this question is important, what you see in this slide is the seasonal climate forecast for the 2012 that was initialized in May, and this is precipitation forecast. And what we find it in the forecast data, there was no indication of such a large scale drought. So almost everywhere you see white. So what does this forecast suggest? That there is a limited predictability of drought in the Great Plains. And this is the work that was published in 2014 from Marty Horling group at NOVA. So the two new results that I'm going to share today with you is, yes, there was no early warning in precipitation, but had we looked into the soil moisture, we could have some early warning for the 2012 drought. And the reason that I'll try to convince you is soil moisture has a higher predictability than precipitation, and that's one of the key results from this study. And then second key result that I will be talking is the land atmosphere interaction played a critical role in that predictability of the drought. So it's likely, like some of previous studies, particularly if you do offline, then offline means land only experiment, that is likely to underestimate the effect of the land atmosphere coupling. And there are a couple of mechanisms why I say so. So these are two main results that I will be talking in next several slides. So what is the key hypothesis here is land processes and their coupled interaction with the atmosphere can enhance the soil moisture predictability beyond what is attributable to the SST forcing alone. So SST forcing, it does provide a portion of the predictability, but we can further add on to that predictability by representing the land atmosphere interaction in the model. There are representation of the land atmosphere interaction in the model. What this talk motivates is we need to keep working on those, improving those interaction, because there are some suggestions that these interactions are not as good as found in the observation. So this is GLACE family of the experiment. A little bit history in the GLACE. GLACE was originally performed by the Randy Koster at NASA back in 2004. This is figure from his seminal paper that came in Science, and that paper was quite a big leap in terms of how we think about the land atmosphere interaction. What this in figure, you see the region where the land atmosphere interaction affected the precipitation variability, and you see all those transition region where we find it is impacting the precipitation variability. So that was original GLACE in 2004. Then in 2009, 2010, it came GLACE-2 that mainly focused on how the land initialization impact the subseasonal forecast around 45 days or 60 days of the forecast. Then 2013, GLACE-CMF5 came, and GLACE-CMF5 was focused on how the climate change effect, particularly drying of the soil moisture, will affect the land atmosphere coupling and its impact on the temperature variability and extreme. So this is a GLACE history. In the same family of the experiment, this fits into the GLACE-Hydrology. This is a combination of 4 different experiments. So what is experiment number 1 is the standard MF type run, means you use the observed SST to run couple land and atmosphere run. In this case, we use CLM5 and CLM4.5, and land and atmosphere are coupled, that is shown here. Both has anomaly. There is a precipitation anomaly followed by the soil moisture anomalies, and then they interact with each other. It's a standard MF type run. Then there is a experiment number 2, where what we did it following the GLACE methodology, we instead of allowing the soil moisture to interactively evolve, we fixed it to the seasonal climatology. So now you don't see the soil moisture variability is here. Precipitation variability is a lot. So this is again, MF type run, but with the prescribed soil moisture. And so this is again done with the CLM CAM5, CLM 4.5, but we, for every time step, we write it down, the soil moisture to its seasonal climatology value. So this is called like uncoupled run or the prescribed soil moisture run. So if we look into only this experiment, what it will give us is what is the impact of land atmosphere coupling on the atmospheric variability, like what is impact on precipitation, what is impact on the temperature. So it doesn't say anything about how does it impact the land variability, like the soil moisture or the water resources. So that's why we added a second component where we save 3 hourly coupler data, basically meteorological forcing data from this MF type run, and then we use that run to drive the land model against CLM 4.5 with the forcing from that coupled run. Similarly, we did for that prescribed soil moisture run, and then can we drive the CLM with the forcing from land atmosphere uncoupled run. So we will call it land atmosphere uncoupled land run, and they will call it land atmosphere coupled land run. So this is the hydrology component here. That's why a name has been added to the GLACE-Hydrology, because this experiment now allows us to investigate what does land atmosphere coupling does to the land variability, like a soil moisture anomaly or the water resources. Some more details, we run it from 1971 to 2014, 44 years. And then we run it 10 ensemble. There is 10 couple ensemble, 10 uncoupled ensemble. And then from each of those ensemble, we save the 3 hourly output, 3 hourly meteorological forcing data, and then we drive the CLM run. So this was, that's where the experiment became quite data intensive, because saving the 3 hourly output for kind of 20 ensemble member and 44-year runs, it's a very big data set. Okay, little more on experiment before I describe. So as I said, there is first of all, the data is we publish the data on the RDA, Research Data Archive. You can find the GLACE Hydrology Experiment. Second one is there is a MF type run. So in the MF type run, when I saw any analysis of precipitation and temperature, that is coming directly from the MF type run. Whereas when I show you any analysis of the soil moisture or ET, evapotranspiration, it comes from that land only run. So there are complications involved. So if you are using this data, make sure you are correctly using the data. If you have any questions, just ask us because we want the data to be used correctly. You will also find a different terminology in the literature, like land atmosphere interaction are mainly referred as the soil moisture and ET correlation. Then feedback is built into the precipitation and temperature. When I refer to the coupling, I mean both. I mean interaction as well as the feedback. Okay, this is the budget equation that I was talking about. What we'll do, we'll start from very basic water balance equation that says change in the soil moisture del S here is equal to precipitation minus evapotranspiration minus runoff. And then we'll do some algebra. What it derives as is the sigma ST. This is a soil moisture variability at time t. Is a function of four different terms. I will describe each term one by one. First one is soil moisture memory. So rho is the correlation. This is like one correlation. So this term is very significant in at least like a couple of different. One is we can get this correlation term or the memory term from the climatological data or the historical data. Then that's one significant. Then the second one is it is multiplied by sigma st minus 1. So to get this term, only we need to know the lag 1 correlation and what was the soil moisture variability at the previous time step. So this previous time step is very important because it is always known at any point of time you go back and at least you apply this equation on the monthly basis because there is an assumption of sigma st is not equal to sigma st minus 1. So we'll call it soil moisture memory term. Let me see. Yeah. So second one is soil moisture and precipitation covariability term. Also, sometime I've been referred like a soil moisture and precipitation coupling term. But until you do lead lag analysis, it doesn't come out to be coupling. But at least because both are concurrent, it is what is correlation at time t of precipitation with the soil moisture. So it is not clear like whether precipitation is driving soil moisture or soil moisture is driving precipitation. Until you differentiate between those two, coupling part doesn't become very clear. So for our discussion, we'll call it soil moisture and precipitation covariability. This is multiplied by the standard deviation of the precipitation at time t. So we need to know from the seasonal climate forecast. And as we'll go into this presentation, we'll see this term doesn't have a much of the predictability. Then going next is the soil moisture and ET covariability term. Again, we need to know the standard deviation of the ET at the time t. So again, it's concurrent term. We can get it from the seasonal climate forecast. And another significance of this particular term is this is what many of the land atmosphere interaction studies generally refer to the terrestrial coupling or land atmosphere coupling by this term. Covariability between ET and the soil moisture. Then finally is the soil moisture and runoff correlation term multiplied by the runoff variability at time t. Again, this term hydrologists deal with this term. So now you see the soil moisture variability is a function of 4 different terms. And what a big takeaway for now, you can take it, but I'll try to convince you in this presentation is soil moisture variance is not simply equal to the precipitation variance, at least for the seasonal forecasting purpose. And that's what a kind of a main message that I'm trying to give through this presentation, and will convince you through numbers that why I'm saying it's not equal to precipitation variance for seasonal forecasting. Okay, so that was more a different term. What do we think about the land atmosphere coupling? Like, what is our concept? If we put open water on the surface, if there is sun, it will evaporate. So basically you think about there is a less of the resistance on the surface, then we can put the water into the soil, put some grasses, maybe it will have some kind of a medium resistance. I'm talking about this RS term here. You put more trees, maybe resistance will increase. So when, at least for this discussion, when I'm talking about land atmosphere coupled system, means land has a capacity to modulate the near surface climate. And one of the thing from this equation, it will come out if we keep increasing the RS here, it will, so it's in the denominator, it will decrease the E, right? So rate of the flow to the ET is the evapotranspiration to the atmosphere. So if we increase the RS, ET will decrease. it is worth mentioning that Daniel Kennedy worked with ASP postdoc here when he put like all those complicated resistance in the CLM5. And if you read his paper carefully, you will find like he finds a decrease in the transpiration because he made the system more coupled land atmosphere system through its plant hydraulic stress parameterization. So that's a kind of key hypothesis. So that was coming from the but like a land surface modeling perspective. Even if you think you come from that Glacier-Clapeyron perspective, and there is very good work published by the University of Washington group, and what they are good is there is a negative feedback between evaporative cooling and the vapor pressure deficit. So vapor pressure deficit is the primary driver of the evapotranspiration. So when there will be evapotranspiration, the temperature will cool down. If temperature will cool down, this particular term QS, that is a function of saturation vapor pressure, is a function of temperature. So this term will decrease. So overall, the vapor pressure will decrease. So evapotranspiration will lead to the evaporative cooling that will decrease the QS as a function of T, and that will decrease the VPD, vapor pressure deficit. So that will also decrease your evapotranspiration. So that also coming from that Glacier-Clapeyron perspective, yeah, rate of water flow to the atmosphere is likely to decrease when you make the system more coupled. Okay, so it was interesting to see like two very different group came up with yeah, very different perspective, but we came up with the same result. What in this plot you are seeing it is the I picked up a region in the central North America, then plotted a difference between coupled and uncoupled run near surface air temperature on the y-axis, and the x-axis is the what was the soil moisture saturation level in the coupled experiment. And what I plotted every point that was feasible for average for the summer. That's to see like, is there any point which gives us a negative feedback? That's why there is a million of the points. But what interestingly you find it, this blue line, that's some kind of a smooth average. Yeah, when soil moisture is drier, it warms up the climate quite a bit. But when soil moisture is more saturated, like saturation level goes to 1, or the wet condition, it crosses over the 0 line. So this is one of the main reasons why whenever you do the land atmosphere coupling experiment, you find the climate become the warmer. Because on this, in the wetter condition, it doesn't impact the climate, at least in the mean sense, but on the drier extent, it warms up the climate. So that was interesting to see, like two different school of thought came up with kind of similar result. Okay, then the second big takeaway from what I just described in the last two slides is, yeah, when you couple the system, its a rate of water flow to the atmosphere decreases. That means ET, we are decreasing it. That means water is residing for longer time in the soil. That means the soil moisture residence time will increase. So this is a plot of the difference in the soil moisture residence time. So what the way this is little detailed calculation, means we save the daily output, and then we go and identify only the non-rainy days, and then we compute what it takes for the e-fall decay time. And you see purplish color means it's increasing, and then whatever green color is there, that means it is decreasing. And for most of the mid-latitude, you see statistically significant increase that is shown by the stippling. But that again proves the point that land atmosphere coupling decreases the water flow to rate of water flow to the atmosphere, and it increases the soil moisture residence time. That is a big takeaway number 2. Now I'll go into some of the result section, just to again to remind everyone it is anomaly coupling that we removed it. So there is no way like we can make fully uncoupled system. What we did remove it, the anomalous part of the soil moisture when we were running the EMF type run. For the most part, I'll be discussing the changes in the variability and predictability. Drought is a manifestation of the soil moisture variability. That's what I'll discuss it. I'll not discuss changes in the mean climate. It was a warmer climate for the reason I explained you earlier. It was a little drier climate. It's very much consistent with the previous GLACE study. So I've not discussed these results in this presentation today. Okay, so now here are the first result. What you are seeing in this slide is the zonal average of the temperature and evapotranspiration variability. All blue lines are the coupled experiment. So each of the 10 ensemble members are represented here, and the red line are uncoupled experiment. So top plot is coming directly from the MF type run. And the top figure is not a new result. This was the result that Delbert and Menabe, he got it in 1988. So this is 30 years old result. Our first goal was can we match their results? Yes, so we were able to match it. So we were happy with that. So what you see here, as found in previous study, land atmosphere coupling increases the temperature variability in low to mid latitude, particularly at the mid latitude. Temperature variability is significantly higher when we do the land atmosphere coupling experiment. A new result here is evapotranspiration variability also increases, particularly in the mid latitude. If you go into 30 north to 60 north, you find there is a significant increase in the evapotranspiration variability. These are all the results for the JJA. When we do DJF, some of these variability shift to increase in the variability shift to the southern hemisphere. So the ET variability, it becomes stronger in the coupled system, and that's again consistent with the soil will receive more water, keep more water by themselves, and that will lead to the increase in variability in both the soil system as well as in the atmospheric system. Okay, the second thing that we found interesting in our experiment was one is ET. Now you are seeing the spatial map of that between coupled and uncoupled run. So in the top, we are seeing the differences in the ET variability, as I explained in the last slide, that ET variability increases for most of the mid latitude, particularly in the transition zone. When you go from wet to dry climate, you see the same increase in the ET variability in the North America, in the Europe. So that's again, there is a spatial signature why we were seeing the increase in the ET variability in the zonal average plot. What second thing we found, that increase in the ET variability mostly is in the mid latitude, but that doesn't translate into the precipitation variability response in the mid latitude. So if we compare these two red regions, ET variability increased significantly, but precipitation variability didn't respond in a co-located way. So where the precipitation variability is increasing, precipitation variability is increasing mostly in the Southeast Asia. not much changes in the ET variability, but there is a increase, statistically significant increase that is shown by the stippling in the Southeast Asia. So what we think that precipitation variability response was more driven by the circulation response, whereas the ET variability response was more of a local response. So one way of explaining the same thing is if you think about how does the land and atmosphere talk to each other, we'll talk from the bottom, from the green box, like land says to the atmosphere that keep doing what you are doing. I'll let you know when I have something to say. That means when it starts becoming spring to summer, then the land fractures start mattering to the climate. It adds to the temperature variability. That's what it means, like atmosphere keep doing all along the year, but from spring to summer, land is started having the influence. So how does the atmosphere replies to the land? Okay, you can keep, you can say when you want, means you can say in the summer what you want to say, but once you have said it, I'll determine what to do with that. Means once land gives the moisture to the atmosphere, it put into its kind of circulation feature, and then wherever it prefers, because of the energetic constraint, it dumps that water. So it took a lot of ET variability from the mid-latitude, but it dumped all those water into the tropics. So that's a kind of one way of interpreting how does the land-atmosphere conversation occurs, or the coupling occurs, at least for the moisture-wise. Okay, let me see. Okay, so now what we'll do is now one of the major term here was the soil moisture variability and how it changed in response to the land atmosphere coupling. You see the plot between of the difference between coupled and uncoupled run, and it's a complex plot to be very fair. We see both increase and decrease. Increase area are generally larger than the decrease area. But sometimes they are very much kind of side by side located. If we focus on these two regions of the United States, one towards a more kind of a Midwest region where we find the soil moisture variability increases, and then more towards the eastern part of that central region where the soil moisture variability decreases. And you see the green color plot. We'll focus on some of these, at least these two regions, to explain you why do we find this complex looking plot in terms of the soil moisture variability. Of course, the soil moisture variability is not only driven by the soil moisture memory. There are other terms, and that adds up to this complex looking plot. Okay, so this is one of the most clean result. Clean result means at least like color are of one sign. So this is your first term on the left, on the right hand side. This is lag 1 correlation. As we expected, the land atmosphere coupling increased the lag 1 correlation. That means memory, particularly some of the central United States region, you will see it's kind of statistically significant. Also parts of that Europe in the mid latitude, it's statistically significant. And it's very similar to the argument that Bertschulli and Battisti made in 1998 in its ocean atmosphere coupling, particularly in the mid latitude. So when you couple the system, it decreases the gradient between ocean and the atmosphere. That means if you decrease the gradient is the driver of the for example, ET fluxes, and then when you decrease that gradient, you allow quantity to reside in that respective system for a longer time. So that's one explanation why we find the increase in the soil moisture memory. So from at least the soil moisture memory side, we can expect the thing of predictability to look better because it increased the memory. And the second term that I wanted to focus on is the soil moisture and ET coupling term. I wanted to focus because this is one of the most extensively studied term in the land atmosphere interaction literature, and as we expected, we do find there is a significant increase in soil moisture and ET coupling, ET correlation, particularly in the mid-latitude region. So that was expected result. What is a second or side interpretation of this result is, if you remember it, it was the same CLM 4.5 CLM land model, but we used two different climate forcing to come up with the soil moisture and ET variability statistics or correlation statistics shown here. So what does that mean? That land atmosphere coupling is built into the climate forcing data. So if I have a 5 different land models and use the same climate forcing to run it, they may show you the similar soil moisture and ET correlation. Whereas if I use the same land model but force it using two different climate forcing, then it may show you very well a very different soil moisture ET correlation. So soil moisture ET correlation is built in the atmospheric forcing, and yeah, I'll leave it there. Finally, yeah, so these are I explained you these two terms. Now we'll see how does this complex looking variability plot is contributed by all these four terms. So A is the memory term. Again, you see the difference between coupled and uncoupled and how much this memory term contributed to the soil moisture variability. As expected, memory term tried to increase the soil moisture variability for most part. Then one of the surprising result was this forcing term. Forcing term is that precipitation variability multiplied by precipitation in the soil moisture. That did not affect the soil moisture variability for most part. And what we think is this is a special since the ET acted in a different region than the precipitation, and that led to this result, like it is not affecting the soil moisture variability. Then soil moisture ET coupling term is mostly decreased soil moisture variability in the mid-latitude, and then soil moisture and runoff coupling term. Again, you see both the sign mostly in the mid-latitude, it tried to increase the variability by keeping more water in the soil, whereas in the tropics, in the soil is kind of saturated. You put the water into the runoff, so it is decreasing the soil moisture variability in the tropics. So, but this is two regions that I was showing you here. But this is Midwest region, this is Central East region. So if you compare particularly the Midwest region, this is memory term was the biggest biggest contributor to the change in the variability due to land atmosphere coupling. Other terms are small. You can also see here the residual term. Residual term are very small compared to the other terms. But if you go to the kind of adjoining Central East region, why does the soil moisture variability decreases? It was mainly contributed by the soil moisture and ET coupling term. So we average the term for the area, and we see there is a decrease in soil moisture and ET coupling here. That contributes to the decrease in the soil moisture variability term. This is what I was trying to convince you in that big takeaway. Number one is the soil moisture variability is not simply the precipitation variability. Although we did not affect this term significantly due to land atmosphere coupling, but other term contributed to the significant changes in both the in the soil moisture variability. So it's a combination of these four terms that gives the soil moisture variability or the soil moisture drought. So even if we may not be able to predict this term, but if we have a better prediction skill in the here we already know it, what is the soil moisture variability in the previous time step, and the other time we will be able, we can predict the drought in a more with a more skill. In our study, what we find it memory and soil moisture coupling term were major term in the mid-latitude region like USA or Europe, whereas the tropics, it was there was a counterbalancing role of the forcing and then the soil moisture and runoff term. So while this particular term has received a lot of attention in the land atmosphere interaction studies, what our study shows is other terms can play equally important role, and particularly that memory part, because it's always known in advance. Okay, so that was a summary. What is its impact on the hydroclimate predictability? Again, I'm showing you the signal to noise ratio. Basically, I express the signal to total ratio. In the top plot, you see the land atmosphere couple experiment, soil precipitation and the soil moisture, and we do find due to coupling both the predictability of both precipitation and the soil moisture increases. So if you compare here, there are not many stippled area in the uncoupled run, but in the coupled run, we see more particularly toward the western part of the United States. And then the second is, it looks like, yeah, soil moisture has a little greater impact in terms of predictability increase. So if you compare here to this plot, we will see more of the increase in the predictability. Okay, so that was what is in the paper, and you see I am reaching the 12:46, so 45 minutes. So that's what happened during the review process. Basically, reviewer become tired, and then he or she said we should publish the drought in the next paper. So we are working on this drought paper. I wanted to quickly cover like a couple of slides because I thought this is an important result, and that's why I'm covering it, but we'll publish in the next paper. So what I wanted to put here is the WMO definition of the drought. You can find on the web. One thing that struck to me is drought is characterized by the lower than normal precipitation. So that, yeah, that's a good definition, but this is not helping much with respect to that drought forecasting. It's a very bad thing. Drought, it caused almost 680,000 deaths only in Africa between 1970 and 2012. So going back to my motivating, can we predict drought? Do we necessarily need a skillful precipitation forecast to predict the drought at seasonal time scale? So to investigate these questions, what I did one is the simple correlation between the MF type run for the precipitation and the soil moisture. For the soil moisture, we have the remote sensing based data developed by the USDA called SMERS NOVA CCI. It is only for the United States, so we'll focus on the analysis only for the United States. So first, again, top panel is for the couple, bottom panel is for the uncoupled, and certainly the land atmosphere coupling increases the forecast skill because now I'm comparing with the observation in terms of the areal extent. It increases for both precipitation and the soil moisture. So there is some suggestion that yes, it can improve the forecast skill even for when compared to the observation. This is a case of 2012 drought. In the left panel, leftmost panel, you see the soil moisture drought in the SMERS NOVA CCI product. We see very much dry. Most of the central United States is less than 1.5 mean standardized departure. And what we find it in the coupled run, yes, there is a significant skill in the coupled run, whereas the uncoupled run, there is no significant skill. So what does it show? Yes, coupling in this case did provide a predictability of the 2012 drought, at least for the soil moisture. So in the next plot, what I already explained you this top panel. In the bottom panel, I put the precipitation, and what we find, there is no skill in the precipitation forecast as consistent with the seasonal climate forecast that I showed you in the motivating slide. So despite no skill in the precipitation forecast, why we were able to predict the soil moisture. So that answered two of the question. Can we predict drought? Yes, at least in some cases for the soil moisture drought. Do we necessarily need a skillful precipitation forecast to forecast drought a seasonal time scale? Yes, if there is a skill in the precipitation forecast, yes, that is very helpful. But that is not a required term, because we know from the literature or from our studies that precipitation forecast doesn't have the skill, at least for the seasonal, at least in the mid-latitude for the seasonal time scale. So we kind of investigated where this predictability is coming from. So we took that budget equation, replaced all those standard deviation term with the standardized anomaly term, and then put these terms from that climatological 30 years value. So you see this is a big term, 0.88. This is variability across 10 ensemble member. And then you take the anomaly of the soil moisture from the previous time step, and then put the other terms too. And what here integrate this term with the previous month soil moisture anomalies and the concurrent month precipitation, ETO and RT forecast from the climate simulation. And what you find this memory term is the biggest contributor. That's what that is what was contributing to the total predictability here. So that's a kind of a second way of convincing in big takeaway is this term can contribute to the forecast of the soil moisture variability. Let me try to close it. Couple of times I presented that result, and then every time I will get asked like, are all the drought are predictable? No, all the drought are not predictable. One specific case I wanted to mention is the 1988 drought. We didn't find any predictability of 1988 drought. If you see the drought here, it's mostly occurred towards the eastern and central eastern United States, and that could be a reason. If I get some more time, I'll try to investigate why this 1988 drought is not predictable. There is some suggestion that if drought occurs in this kind of bluer area, it's less predictable, whereas if drought occurs in these red areas, that drought is more predictable. So this is again residence time metric, and CLM does a reasonable job. So in all those circles, you see the observation estimated from the North American soil moisture database, and they did a good job. So here are my conclusion. Land atmosphere coupling increased soil moisture memory in the mid latitude. That was the most clean result in the boreal summer. It also increased the evapotranspiration variability throughout the mid latitude, particularly in those transition regions. Third key result was ET variability and precipitation variability were not spatially co-located. That's a different result. Min Lo from National University of Taiwan, he's working on another follow-up manuscript to explain some of these findings. Overall, we do find land atmosphere coupling improves predictability, and it's through a combination of the effects on the memory term, precipitation variability, soil moisture, ET coupling, and runoff soil moisture and runoff coupling. For the Great Plains, for the 2012, we did find predictability come from these combination of these 4 terms. Okay, so this is I got started in this project from the associate board at the NOVA PSL, CISL. They were very supportive. They kind of at one time I told them like pipe ensemble is not sufficient, and they again gave me kind of $1 million of code hour to do this project. Eric Krujek, I almost hijacked his office hour for 2 weeks to do this project. And then when I moved to the Auburn, they gave me some supplemental USDA hedge funding to do this work. Thank you.
Thanks very much, Sanjiv. That was great. I see some virtual applause in the participants window. I particularly liked your analogy of the land and the atmosphere talking to each other as a conversation. I thought that was great. So if you have questions for Sanjiv, feel free to use the raise hand feature, or you can type your question in the chat. And I see that Isla has a question. Go ahead, Isla.
Hi, yeah, thanks for the talk. When you showed the influence of the land atmosphere coupling on the temperature variability, there were big changes in the low latitudes of the Northern Hemisphere where it didn't seem like there were changes in the evapotranspiration variability. I was just wondering what was going on there. Was that related to those precipitation changes in Asia, or?
Yeah, that's a very good question. So you are referring back to
the line plots.
Yeah,
those ones.
Yeah, why it didn't change in the tropics, the evapotranspiration variability. So if I were to say like tropics doesn't have like kind of lot of seasonal, means evapotranspiration has a lot of seasonality in the mid latitude. So you get very high evapotranspiration during the growing season. But tropics has like a more of a temperature that let the evapotranspiration occur for most part of the season. That may be partially contributing it, but I've not investigated this issue.
So what would cause the temperature variability changes if it's not the evapotranspiration? It would be not like influences on the atmospheric circulation, or?
Yeah, what would cause the in the low latitude? Yeah, to say something concrete, I need to investigate it.
Okay, thanks.
Thank you.
Looks like there's a question or a comment in the chat from Imtiaz. Based on your results, looks like water limited regions have greater soil moisture memory effects and therefore probably have greater soil moisture predictability. Did you want to comment on that, or Imtiaz, if you want to unmute and add any context as well?
No, if Sanjiv wants to comment to that, that'll be great. Sanjiv, I just found that, I mean, just looking at some of your last slides where you're showing that the western part of the US had greater soil moisture memory effects. And I was just wondering if there is a clear signal that you're getting between these energy limited regions on the right, on the east, and kind of the water limited region on the west. And which may be a good thing if you have greater predictability for these regions that are more susceptible to droughts. Actually, that's an added value to your framing.
Yeah, thank you. Yeah, that's a good question. And we did some of the analysis that we'll put in the drought paper. And yes, there is a suggestion that if as the memory increases, the predictability increases in that dry part of the region, and dry part has generally greater memory than the wetter part, where it's like, yeah, so I'll keep doing, and then precipitation comes in and it destroys all the memory. So we'll put some of these analysis in that second follow-on drought paper. Thank you.
Great. Maybe we'll take one more question from Youssef in the chat. What do you expect for hyper-arid desert environments with limited vegetation and thus evapotranspiration? Would surface evaporation alone explain changes between the coupled and uncoupled configurations?
Yeah, thank you for that question. And we do see some interesting result, at least for the soil moisture residence time. You see that hyper desert region where its soil moisture residence time is decreasing. And we suspect that this is due to increase in the precipitation variability in those regions. Then the land atmosphere interaction processes, but we did not get time to see those super dry regions. But there are there are interesting and statistically significant features, as you can see in the southwest part. Even for we go to the Sahel, Sahara Desert or Arabian Peninsula, there are some interesting results there.
Great. Thanks very much, Sanjiv. Thanks everyone for the questions. So we will see everybody next week. We'll hear from Zane Martin from CSU, who'll be giving the seminar next week. Thanks again, Sanjiv. Thanks everyone.
Thank you. Bye.